Janet visiting us for this week. She'll be here until Wednesday, so if you have questions, keep that in mind. And she will tell us about her work on thermodynamics and Rainy Entropy and applications.
Thank you. Thank you very much for giving me the opportunity to speak here. So I will be talking about the thermodynamics approach to understanding entanglement entropy and Rainy entropy and some of the applications. So this is work initially developed by Rob and his collaborators, Cassini, Herta, and then the applications part is work with, I'm involved in work in the applications part with Rob and lots of friends. So, so this is the outline of the talk. So first of all, in case you're not already familiar with Rainy entropy and entanglement entropy, I'll give some introduction to these objects. And then I will review this nice story of the thermodynamic approach. And then we'll look at various applications that we built recently. And to see that this approach is a very powerful way to understand Rainy entropy and entanglement, particularly in conformal field theory. So to start with, some background. The entanglement entropy is basically a quantitative measure that people come up to measure quantum entanglement. It turns out that it is a very good, it is useful in many other places, such as being an autoparameter of phase transitions, like in detecting confinement. And more recently, people realized that it could also detect topological phase transitions involving topological phases, where conventional autoparameters are not available. It is also a very interesting probing dynamical process of thermalization of a dynamical process, relaxation in a dynamical system. In numerical work, it is also very useful. For example, to tell how easy a wave function can be simulated on a computer, the entanglement entropy is a good way to tell. And also, in d equals 1 plus 1, it is the best way to extracting the central charge of a CFT numerically. So, let us remind ourselves what the entanglement entropy is. So, to compute the entanglement entropy, we have to introduce this object called the reduced density matrix. The reduced density matrix is built on a state, let's say we're given a quantum state psi. We could build the density matrix rho. And suppose we choose a region A in phase space, then the reduced density matrix of A is defined as the trace of rho over all of space, all of the complement of A, that we call B. And the entanglement entropy is defined as the von Neumann entropy evaluated on rho A, which now looks like a mixed state. So what exactly is the Rainy entropy? The Rainy entropy is just defined as log trace rho A to the power n divided by 1 minus n. As background story, Renyi was trying to look for some general notion of quantum measure of quantum entanglement, not quantum, general measure of correlations in information in the context of information theory. And he found that a very general, a very natural generalization of the von Neumann entropy. In fact, the entanglement, the von Neumann entropy itself can be thought of as a limiting case of the Rainy entropy, where you take n to 1. In the limit n to 1, you basically recover the entanglement entropy. And in fact, we will be focusing mostly on computing Rainy entropies and entanglement entropies in field theories. And to compute, in the case of field theory, where rho A is really an infinite dimensional matrix, computing first the Rainy entropy and then taking this limit is in fact the easiest way of actually computing the entanglement entropy. And this is often called the replica trick, where we're introducing n replicas, as we will see. So now, why do people care about this Rainy entropy at all? The first reason is that it is just easier to compute, as I just mentioned. This is, in fact, a trick used to computing entanglement entropy. it is not hard to see that the Rainy entropy decreases with increasing value of n. So if you're computing, let's say S2 gives you a rough estimate of the entanglement entropy, gives you a bound. It also allows one to infer the full complete spectrum of the reduced density matrix, and this turns out to be particularly useful if you're talking about topological phases in matter. It was demonstrated that the spectrum of the reduced density matrix can in fact turns out to be the physical spectrum in the edge states of some topological phases demonstrated by Haldane and also by others. So and there are other uses of the Rainy entropy, such as if you are computing it in a finite size system, it could tell you something about the lowest irrelevant operators. In all these applications that we will be talking about, in fact, we will be computing Rainy entropy or entanglement entropy in configuration space. We're looking at quantum entanglement in configuration space. So the setting of our problems is we are looking at quantum field theory in d-dimensional flat Minkowski space, and we'll be particularly looking at the ground state. The region A would be chosen as some spatial region in configuration space. So A would be d-1 dimensional, and the boundary of A is d-2 dimensional. So it's a codimension 2 object. It will play a very special role, and so let's give it a special name, the entangling surface. So the bottom line is, if we are computing Rainy entropies in the context of field theory, we will be computing a path integral. And this path integral boils down to evaluating the path integral on a singular manifold. And this singular manifold has conical singularities localized at the entangling surface, the boundary of A. Yes?
So is the region A itself d-dimensional, or it's some infinite dimensional region in some Hilbert space?
A itself, it is infinite dimensional from the point of view of Hilbert space, because we are dealing with a field theory. But here, we're talking about some spatial region in space-time, in space.
How do we associate then this A with a spatial region?
A is literally a spatial region. Of course, you could have, in field theory, you could have different modes excited at different points in space-time. You could build your Hilbert space in space-time, but A itself is really just space, part of space. You choose a region in space, and you integrate all degrees of freedom outside of A. That is what you try to compute here. So let me just show you a picture of what the path integral looks like.
And why do we have conical singularities suddenly in this story?
Right, so I'm showing why that
okay.
is.
Sorry.
So let's suppose, so how to compute this path integral in practice? Let's say n equals 3, and let's say we're in 1 plus 1 dimension, and region A would be just one interval, one line bounded by 2 points, and I call U and V. So let's say n equals 3. So I introduce 3 copies of space-time, and what this trace is doing, this matrix product is doing, is that I split this interval into 2 lines. One at time equals t 0 plus, and one at time equals 0 minus. And the matrix product is telling you to identify, to do some very special boundary conditions. Along A, I identify I make boundary conditions on the fields such that those at within A at 0 plus is identified with A on 0 minus. These dotted lines are the identification boundary conditions along A. I keep identifying until I reach the top copy. Then I identify A at 0 plus back with A equals 0 minus at the bottom copy. And so you could see that if I move around a point U at the boundary, I have to move around it 2 pi n before I reach the starting point again. And that is where the angle excess comes from. And therefore, there is a conical singularity located at the boundary of A, the entangling point now in 1 plus 1 dimension. But in higher dimensions, this would be a codimension 2 defect, or codimension 2 surface in higher dimensions. We can see that this is in general a very difficult problem. It's very difficult. Even in free fields, it's not a trivial thing to do a path integral in a complicated geometry as such. So one might wonder, is there a way to do it holographically? You could imagine if I want to look for a holographic dual of the replicated geometry in the boundary, that is not a trivial thing at all. But then these people, Ru and Takenagi, they came up with a completely intuitive guess. They say that the entanglement entropy of a field theory with a gravity dual is given by the area of some minimal surface divided by 4gn. What is this minimal surface? This minimal surface is some surface that extends into the ADS mode such that at the z=0 ADS boundary, it connects to the boundary of region A, the entangling surface we have been talking about. And since the introduction of this formula, remarkably, it has passed many non-trivial tests, and more remarkably, it was proved by these people only a few months ago. But even with this proposal, it is not by any means straightforward or clear how to generalize this kind of computations to more general gravity theories, or to compute Rainy entropy for general n. If I'm interested in the spectrum, I'll be interested in general n. And in holographically, quite ironically, we can compute S1, but we can't compute Sn. Sorry.
Well, in what context did the Thomas and prove it?
So they were trying to look at the case where n is sufficiently close to 1. And so they are trying to think about extending the conical singularity at the boundary into the bulk.
I guess I was asking more like for general ADS CFT for any.
It's a general ADS CFT, it's not just for pure ADS. Okay, so that now having given some background about this topic, let me go to the story of how to reformulate the problem as a thermodynamic problem, and to see how that helps us in understanding how to compute this quantity and what they're useful for. So, okay, so now let's go back to the reduced density matrix rho A, and let's completely trivially rewrite it in terms of some operator that is algebraic QFT people like to call modular Hamiltonian. So this is just a formal way of rewriting things. But if I do that, then you could see that when I compute the correlation functions using the reduced density matrix rho A, there is a U1 symmetry, simply because translation using this H operator just trivially commutes with rho A. Also, you could see that if I if I take S to be complex, there is a periodicity in S in the complex time. Let us call it time. There's periodicity in S again, simply because it commutes with rho A. So it looks like we're dealing with a thermal problem with some inverse temperature that we could set to 1. So if we are computing the Rainy entropy, then we'll be taking rho A to the power n. So it would turn out that we'll be looking at a problem with temperature, inverse temperature n. But so far, it is totally not useful, because H, what exactly is H? We have no idea. And in general, it's just some non-local, some stuff. And so it doesn't seem to be particularly powerful. But in some cases, we actually know what H is. So for example, if you're considering a relativistic QFT, the famous example is to think about accelerated observers. It is well known that an accelerated observer is only causally connected to regions within the Rindler horizon, and that region is called the Rindler wedge. These two are the Rindler horizon, and the accelerated observers is bounded by the Rindler horizon. Using proper coordinates in the rest frame of the accelerated observer, it is useful to introduce these coordinates. Tau is the Rindler time, the rest the time in the rest frame of the accelerated observer, and this R is basically the inverse acceleration of the accelerated observer. And it is also well known that an accelerated observer experiences an apparent thermal state. Why is that? That's because his density matrix is exactly a reduced density matrix where half of the space outside of the Rindler horizon has been integrated out. And so his reduced density matrix, his region A, is precisely this half of the space x greater than 0. And in this case, what is the modular Hamiltonian? The modular Hamiltonian is the Hamiltonian that generates his time translation. And the temperature, the scale of the temperature is set by inverse of his acceleration. So we have one nice example. In the case of conformal field theory, things are even better. And the reason is, let's consider a region A that is actually a ball that bounded by a d-2-dimensional sphere of radius r. In this case, there's a special region called the causal development of A, such that within this causal diamond, every point in the causal diamond is only causally affected by A. And it is observed that there is a conformal transformation that takes this causal diamond into the Rindler wedge. Therefore, if I'm computing trace rho A to the power n in the conformal field theory, I could just replace this computation with taking the reduced density matrix of an accelerated observer in the Rindler wedge. And this is a well-known object. And acceleration is simply, the scale of the acceleration is simply set by the radius of the sphere. And this is true only up to conformal anomaly, which is well controlled in the conformal field theory. Okay, so now it is also convenient if I make a further bio transformation, a bio rescaling, and which take us from the Rindler wedge to a d-1 dimensional hyperbolic space times r. R is really the time direction tau. This bio rescaling is really simple. As we will see in later slides, it is also useful to go from these Poincare coordinates into global coordinates. In any event, the modular Hamiltonian of this spherical, of this ball regions bounded by a sphere, is basically the Hamiltonian in this hyperbolic space generating time translation with t tau tau. And if we follow through the bio transformation, it turns out that it is just the stress tensor, the energy density in Minkowski space, multiplied by a simple bio factor. Okay, so all of this discussion is good for any conformal field theory. We haven't specialized in, we haven't said anything about what happens holographically, and this picture is just true everywhere. We have reduced the computation of Rainy entropy of a general conformal field theory into computing thermal properties of the same theory in hyperbolic space. And the fact that when we introduce different ends, the Rainy entropy can be rearranged. This part is just the proper normalization that I haven't been careful about in previous slides. The Rainy entropy can be rearranged into the form of the difference of free energies evaluated on hyperbolic space at two different temperatures.
And with this proper normalization, this object is actually regularization independent?
This object is UV divergent. So
even with the subtraction?
That's right.
Uh-huh.
And I will show you that this UV divergence is a good thing. People do know something about how it should diverge, and as we just demonstrate, by looking at it from the point of view of as a thermal problem, we could reproduce all of these properties that are well known now for these Rainy entropies. Okay. So just a little bit more rewriting. Since the Rainy entropy is a difference of free energies, you could also express it in terms of integrating the thermal entropy in hyperbolic space, thermal entropy density in hyperbolic space, which we these two temperatures. And since everything is homogeneous, the thermal entropy, thermal entropy density does not depend on space-time coordinates, and so the volume of the hyperbolic space simply factors out. And this comes to the point. Hyperbolic space has infinite volume, so what exactly is this we doing here? There's an IR divergence. But this IR divergence is actually expected. We are expecting it to appear. Why is that? So let's try to come up with a good way, a sensible way to regulating it. The point is, if we go through the conformal transformation, there's actually a compact way of writing down these conformal transformations from flat space coordinates to these hyperbolic space coordinates. It's just, if we introduce a complex coordinate, it's written in this form. So recall that in the flat space, in Minkowski space, by introducing n copies, there is some conical singularity localized at the entangling surface. So the entangling surface is located at little r equals r. So what happens from the point of view of u? If you move little r close to r, u is actually going to infinity. Therefore, the UV divergence that we're expecting as you move close to the conical singularity is now turning into an IR divergence as an IR divergence of the hyperbolic space. So now it gives you a very natural way to regulate it. So all you need to do is you want to stay a little bit away from the conical singularity, and that distance, let's call it delta. And you could make use of the conformal transformation and interpret that as some bound on the value of u. You don't want to get too far into, you don't want u to get too large. And in that case, if I plug these expressions back into the volume factor of the volume factor of this hyperbolic space, it turns into this form. And this term is the famous area law of entanglement entropy, also for Rainy entropy. That it is well known that entanglement entropy in the local field theory is simply is a UV divergent quantity, and the leading UV divergence is proportional to the area of the entangling surface. This is basically roughly due to the fact that all entanglement the leading contribution to all entanglement came through the surface that separates your region A from the rest of the world. And in even dimensional theories, you also get a logarithmic divergence, and this is related to conformal anomaly, and this C is related to central charges of the CFT. So the thermal picture very naturally reproduces some known feature of entanglement entropy, Renyi entropy. And so how does that? So now let's go to some applications of this picture. To start with, it immediately gives us a way to compute Rainy entropy holographically. So we didn't know how to obtain the gravity dual of this complicated replicated geometry. But now in the thermodynamic picture, we're just dealing with something at finite temperature in some ADS space. So all you need to do holographically is to find a black hole solution such that at constant radial slices, each slice looks like HD minus 1 cross R. And these solutions are known. So for example, this is the solution in Einstein gravity, and the Rainy entropy simply becomes computing the thermal entropy of a black hole solution and integrated between these two temperatures. The temperature clearly is given by the Hawking temperature of the black hole.
Sorry. So, what's the logic here? You're taking the minimal surface proposal.
We are forgetting about the minimal surface proposal,
right,
and use our new knowledge through the thermodynamic picture and use the conventional dictionary of ADS-CFT to compute Rainy entropy, bypassing the minimal surface picture.
So before you had a picture where you were computing this Rindler wedge, and then you mapped that to hyperbolic space.
Right.
Okay, there I'm with you. So how do you make the jump to ADS now?
Right, so we have a thermal problem
Yeah.
in hyperbolic space. That hyperbolic space is still conformally flat. It is barely related to flat space. And so we know how to do ADS-CFT on curved space. What you do is, if suppose you give in some particular geometry, it means that the boundary geometry of ADS reproduces this geometry that you live in. And that also, at the same time, I'm at finite temperature, so the ADS ball has a black hole. And so it boils down to finding solutions with this slicing. At each constant radius slice, it reproduces the geometry that you live in, and that it has the Hawking temperature that reproduces the temperature that you're interested in. Okay, so these things can be computed. And one nice feature is that what happens at n equals 1? At n equals 1, the conical singularity should go away. And at n equals 1, I'm computing the entanglement entropy again. And from the point of view of the black hole, I'm computing the black hole entropy at n equals 1. And so the black hole entropy is just the area of the horizon divided by 4GN. And since at precisely n equals 1, from the point of view of the boundary geometry, you're not actually introducing conical singularities. The conical singularities disappear. This black hole is also a fake black hole. It is just a different coordinates of pure ADS space. So you can follow through the coordinate transformation that takes you back to Poincare coordinates. And this fake black hole horizon actually is identical to the minimal surface. It's identical to the minimal surface such that it connects back to the entangling surface and the boundary. And therefore, this is in fact the first proof within, if you believe in ADS-CFT, this is in fact the first proof that the Ryu-Takenagi formula is correct. It reproduces what we know of black hole physics. Also, within this picture, it is also very easy to generalize these computations to more general gravity theories because of the Wald entropy formula. Another comment that is in place is that previously we were worried about finding the gravity dual of this complicated complicated conical geometry in the boundary, but now we have a very simple solution to that. It's just these hyperbolic black holes, and at different temperatures, the different temperatures is the different periodicity of the time direction. And so what exactly is happening is that if you look at a cutoff surface near the ADS boundary, there is a conical singularity at the cutoff surface because of the choice of the periodicity of the time direction. But the whole solution itself is smooth. This singularity only occurs at the boundary.
This procedure works for computing the entanglement between for the vacuum. What about the exciting states?
I'm going to actually, okay, I don't know how to talk, to really do excited states, but I have something to say about it later. So, okay, so this is some work we did. We tried to compute, so we computed some entanglement, Rainy entropy in Einstein gravity. It is not very illuminating at this point. At the end, it's just some complicated functions in the Renyi index and the dimensions. But in D equals 1 plus 1, where the dual is an ADS3 hyperbolic black hole, which is actually equivalent to the BDC black hole, the result is very simple. And in fact, it is in complete agreement with the well-known result, which is just proportional to the central charge divided by 6, 1 plus 1 over n. So at least that is a check that we're doing something sensible. So as promised, we could do it for more general gravity theory, so we tested it on Gauss-Bonnet gravity. And again, it's some complicated things. In Gauss-Bonnet gravity, you have two parameters to play with. You could change the two in D equals 4, for example, you have two central charges. And so by changing the Gauss-Bonnet coupling, you could change the central charge. But it looks like the Rainy entropy has some complicated dependence, and probably this result is not universal. It probably doesn't apply to general conformal field theory, this dependence on A and C. But there are some well-known inequalities that is known to be satisfied by the Rainy entropy in the literature. And from the point of view of these black holes, it becomes very natural because they simply follow from the fact that the black hole entropy is positive and heat capacity is positive. So this is so this is one nice feature of our computation. And
So, can you, does this, for example, give you constraints on A and C of the sort that Maldacena and Hoffman derived?
not in
years
this
ago?
case, because
Okay.
it turns out that that bound is much stronger than this
Uh-huh.
bound. So within the window that the theory is known to make sense, everything just
Everything
works.
makes sense.
Yeah.
Uh-huh.
But then, so far we have been dealing with spherical spherical regions, regions bounded by spherical surfaces. So it would be nice if we could infer something that is good for other regions from this picture. And that we have to introduce the notion of surface operators. So in the case of d equals 1 plus 1 dimensions, it is well known that the path integral that we are dealing with these non-trivial boundary conditions along the entangling, non-trivial boundary conditions around the entangling points. You could you could actually deal with this by inserting so-called twist operators that generate these cuts in space-time. And these twist operators are known explicitly in many conformal field theories, and they are primary operators. So the computation of the Rainy entropy basically boils down to computing the correlation functions of these twist operators, and the value of the Rainy entropy is completely controlled by the conformal dimensions of these twist operators. So this picture can actually be generalized in higher dimensions. Of course, in higher dimensions, the explicit construction of these twist operators is not very understood. But then people have argued that if you just assume that these operators exist, you could reproduce most of the features that is known about Rainy entropies. And also, people have thought about, in high dimensions, the entangling surface would be an extended object. Therefore, there would be an extended object for dimension 2 wrapping the entangling surface. And people have thought about properties generally of surface operators. For example, Kapustin, it defined what he called the generalized conformal dimensions of a surface operator, and he studied this stuff by inserting the stress tensor sufficiently close to the surface operator, and simply from the fact that if you're sufficiently close to the surface operator, you don't have to worry so much about the curvature of the surface. Therefore, there would be a lot of symmetries in the problem, and simply from symmetry considerations, you could write down the form of the leading divergence of the correlation functions, and he defined this constant that controls the leading divergence as what he called the conformal dimensions. So this object does not depend on the shape of the surface operator, and therefore, if the Rainy entropy could be thought in terms of these surface operators, we could extract these numbers very easily from the point of view starting with spherical regions.
Sorry, what's the difference between the two formulas you had? A, B,
Oh,
and
this
IB?
along the directions tangential to the operator, and these
it's
are
the normal.
of Okay, so let's do that. And if you follow through the conformal transformation between Minkowski space and hyperbolic space, it turns out that the Rainy entropy, the conformal dimension of this surface operator corresponding to the Rainy entropy is simply the difference in energy densities evaluated at two different temperatures. You could think of this guy as subtracting the contribution of the conformal anomaly as you make the conformal transformation between flat space and hyperbolic space. And for example, we have computed it for many different gravity, this object for many different gravity theories. So again, it doesn't look very illuminating, but when we take the limit n to 1 and take a derivative of this h, we just found that it is always proportional to the central charge of, in fact, the two-point correlation function of the stress tensor. And after a moment's thought, we realized that you could actually prove it completely generally from the point of view of the conformal field theory. So the lesson is that so we could extract conformal dimensions of these surface operators corresponding to Rainy entropies using a spherical entanglement region, and we could extract the and these log divergent and these conformal dimensions. It has been conjectured in the past that it is related to something called Grand-Witten anomaly, and we just show that they are not related in this explicit calculation. And one other lesson that we have learned is that if you make an expansion in n-1, you can find that if you expand the conformal dimension as power series in n-1, the first few terms are completely universal. They're just determined by 2 and 3 point correlation functions of the stress tensor. So HN is actually has some nice universal properties in the general conformal field theory. Okay, so at this point we have been using the thermal picture to try to learn things about, we have been using the thermal picture and do stuff holographically and try to learn things about Rainy entropies in the conformal field theory. So now let me try to say something about what could be done if you start with what we know about Rainy entropies and entanglement entropies in a field theory and see if we could learn something about a gravity theory. And this is and it turns out that actually the Rainy entropy and entanglement entropy in general seems to know a lot about gravity. And I'll show you why. So in order to do that, let me introduce another measure of entropy that is closely related to entanglement entropy and Rainy entropy. And that is the so-called relative entropy. So the relative entropy is evaluated on two density matrices, ρ1 and ρ0, and it's defined as follows. It is not hard to show that it is a positive definite quantity, simply from the fact that ρ1 and ρ0 both trace to 1, and that their eigenvalues are positive definite. And the inequality is saturated if and only if ρ1 is actually equals to ρ0. So if people in quantum information theory frequently takes this as some measure of distance between two probability distributions. So for us, let us try to consider ρ0 to be the reduced density matrix of ground state. Again, region A is chosen to be a sphere, and so we have good knowledge about what the modular Hamiltonian is. And now let us consider ρ1 to be some excited state. And this excited state, we also take a trace over a region outside of A and compute the reduced density matrix of this excited state. So the question is, so now with the knowledge of the form of ρA in terms of the modular Hamiltonian, we could plug it into the formula for the reduced density matrix, and it simply reduces to this form. What is that? That is the difference in the expectation value of the modular Hamiltonian between these two density matrices, subtracted by the entropy evaluated on these two matrices. And that is simply the difference in free energies of ρ1 subtracted by the free energy of ρ0, and it has to be positive definite. So you could think of that as ρ0 is the thermal state with respect to H. So it is it has the minimal of free energy compared to all other states. So you could ask the question: is this inequality satisfied holographically? So let's try to check it. How do we check it? So H is something simple in terms of the stress tensor. Let's consider ρ1 to be an excited state such that the stress tensor has a non-trivial expectation value. This is something that we could choose completely arbitrary. So this side can be computed, can be set, can be fixed from the point of view of the field theory. The entanglement entropy, the entanglement entropy can be computed using the Ryu-Takanagi formula in terms of minimal surfaces. So all we need to do is find the geometry dual to rho 1 with some excited, with some non-trivial stress tensor, and then compute the change in the entanglement entropy using the root-Takanagi formula. And we could plug it into this and see if it is satisfied. In particular, there is a very, very strong constraint in this calculation. What exactly is that? So this is a positive definite. So suppose rho 1 is very close to rho 0, and we could expand rho 1 around rho 0 perturbatively. Then it better be true that the inequality is saturated at linear order in the perturbation, because we cannot have any linear dependence in the perturbation parameter to keep the inequality true in all orders of the perturbation parameter. So in particular, we expect that there's an equality between the change in the expectation value of the stress tensor and the the change in the minimal the area of the minimal surface holographically. So this is a very strong check, because the stress tensor can have arbitrary dependence on space-time coordinates. So let's try to do that holographically. So to do that, it is most convenient to go into 5 milligram coordinates. For rho 0, we simply have the metric of pure ADS space. For rho 1, we are introducing some boundary stress tensor with arbitrary x dependence. And we could make use of the usual ADS-CFT dictionary and construct at least to linear order in this perturbation parameter epsilon, the change in the metric. In general, these Tn coefficients, when n is greater than 0, they are solved using Einstein equation, and they would look roughly like box n time acted on the TAMU, the boundary stress tensor when you put it. Then we would like to compute the change in the entanglement entropy, and the change in the entanglement entropy is the change of the area of the minimal surface. So in a suitable gauge, the minimal surface looks like this, and these z's are solutions to the equations of motion that you obtain from minimizing A. And that what it tells us is at least up to linear order in epsilon, we don't have to worry about changing the profile of the minimal surface. To linear order, the change in the area of the minimal surface came purely from the change in the background metric. So let's do the calculation. It turns out to be much easier to do it in Fourier space, Fourier transforming T, and these coefficients came from Einstein equation. And this is basically the root-Takanagi formula to linear order in epsilon. And from the point of view of the field theory, we have made a choice of T mu nu, and so the change in the math is simply given by this simple object. They look completely different, but somehow you could prove that they're the same. So I think this is a very strong constraint from the field theory, and miraculously it is satisfied by Einstein gravity. I think more remarkably, it was proved by these people a couple of weeks ago that suppose I take that as a requirement that to linear order delta S is equal to delta H. It actually implies linearized Einstein equation. So relative entropy knows about Einstein equation, and I think that is quite remarkable. If you go into try to compute second order in epsilon, go into one higher order, we couldn't do that for completely arbitrary T because the change in the profile is too difficult to solve. But at least for constant T, you could demonstrate explicitly that the inequality is satisfied by Einstein gravity. You could also check if you have other perturbations other than the stress tensor. If suppose you have scalars, vectors, and all of this gives you something sensible, the inequality is in fact satisfied. So before I end, let me try to play some other games to see how much we could learn, what other constraints that one could get from playing with relative entropy. For example, you could consider an annulus region. So in one dimension, this would become two separate two separate intervals, but in high dimensions they could be connected. You could think of them as concentric spheres. And the region that I'm interested in, is the region between two concentric spheres, one sphere of radius r2 and one sphere of radius r1. This vertical direction is the ADS radial direction, and these are minimal surfaces that connect to the entangling surface at the boundary according to the Wu and Tantanagi proposal. So it is well known that if for sufficiently small r1, if you take if these two regions get closer and closer together, there's phase transitions in the minimal surface. It goes from minimal surface that are disconnected into one that is connected in this form. So we know holographically that the area of these two disconnected spheres is related to the stress tensor in such a way we proved it, at least to linear order in perturbing the stress tensor. But then we also know that it has to be related to the modular Hamiltonian of this annulus-like region. Well, for annulus-like region, we don't exactly know what the modular Hamiltonian is. This is a mystery, but it is proved by some algebraic QFT people that this has to be constructed by operators living only within A. It might not be a local expression, but it has to be constructed by operators only within A. So this gives us some very non-trivial looking constraint in the appearance of the allowed appearance of energy distribution. Somehow, so H should be something that is related to the stress tensor within A. And this expression somehow has to be related by energy density that is outside of A, because here in this part of the minimal surface, it is dependent on the stress tensor lying here, which is outside of A. So it's kind of say that if I have some excitations within A, somehow I'm forced to have some other excitations outside of A in appropriate places to make this equality to work. But this is just the first step that one of the games that we try to play with, and it seems that there are lots more things that one could extract out of this. So before I end, I would also like to advertise some other things that we could do with that is inspired by the thermodynamic picture. So here I have been talking about computing Rainy entropy using hyperbolic black holes in using ADS-CFT. So of course, in this case, I only have temperature to play with, but holographically, it's very natural to introduce charged hyperbolic black holes. So it is very tempting to generalize the definition of Rainy entropy and entanglement entropy such that the reduced density matrix is deformed with some chemical potential in hyperbolic space. What that amounts to is that this charge operator is the charge operator in hyperbolic space. If you follow through the conformal transformation, it is the charge density inside region A, and mu is basically turning on A tau. But A tau is a contractible circle. So what we're doing is that by introducing this deformation to the reduced density matrix, I'm inserting some flux localized at the entangling surface. So you might ask, what is this good for? We're not entirely sure yet. We computed these things also in some free theories, and they look qualitatively similar to what we get holographically. And we're hoping that by adding in a chemical potential and the charge operator, we are trying to probe something that has to do with some Euler symmetry, some symmetry. So we're hoping that perhaps this is good for detecting maybe some symmetry. There are some topological bases with symmetry. So maybe this is an object that could help probing these bases. but this is still work in progress. So let me, but I would like to emphasize that all of this is inspired by the thermodynamic picture, which I find it a very powerful way to understanding the entanglement entropy. So to conclude, I hope I've convinced you that this is the thermodynamic picture is a very powerful picture, and the power came really from knowledge of the modular Hamiltonian, or people might call entanglement Hamiltonian, has a local form, particularly if you have if you're dealing with conformal field theory. And this kind of interpretation has led to holographic calculations, which is really one of the few such calculations that you could do beyond free field theories. And I have also demonstrated how, by looking at some other entropy, some other interesting measure of entanglement, it seems to have very non-trivial constraints on the gravity theory. And we could also obtain information about Rainy entropy and entanglement entropy beyond spherical regions. There are some universal properties that we could extract simply using spherical regions. And so it might be interesting in the future, maybe there is some analogous formula, like the Ryu-Takanabe formula, that could compute deformed entanglement entropy. And perhaps it is good for detecting exotic phases in condensed matter. But I think the most interesting part is really to see if the entanglement entropy could give us more non-trivial constraints in gravity. For example, Takanabe, he has been interested in formulating the problem of gravity from using entanglement entropy as the probe of degrees of freedom instead of the metric. He tried to reformulate things in terms of entanglement entropy, and I find that very amusing. Very much.
Great, thank you. So, questions?
So should I think of this entropy as a thermodynamical entity, or can I use it in local field theory? I mean, your last remark suggests that it doesn't have to be thermodynamical, really. I can use it for gravity, which in some sense is, say, you could call it a local field theory independent of finite temperature.
No, we don't know the value for entanglement because it's UV divergent.
UV divergent. Well, I have in mind, your last remark is very interesting. Getting the observables in gravity from this entropy.
Right.
Can you comment a bit more on this? Because in ADS gravity, for example, you calculate Witten diagrams to get the perturbative meaning of correlation functions in gravity, right? That's what we do.
Right.
Whereas the object you described, if you were to use it in quantum gravity, would it go beyond perturbative quantum gravity in ADS?
At this point, it is completely. At this point, what people actually did is to try to see how Einstein gravity turns into equations for the minimal surface. So we haven't really completely got rid of the metric.
But even skipping that step, can you make connection with the result that you get for the S matrix elements? If you calculate correlation functions, endpoint functions in ADS, can you connect it to this object?
I think people haven't really done much there, but the hope is that it could, that you could, instead of using the metric, you could rephrase everything in terms of some entanglement metric. But this is, I think
It's the hope, it's not done.
It's just, it only started, I think, at most less than a few months ago, so it's...
Ooh, really new.
Yes.
By any standard. Okay.
Other questions?
So someone has compared the entanglement entropy for higher spin theory.
Yeah.
And can one use energy while higher spin theory?
I think it is possible. I'm quite encouraged by the fact that we could obtain Einstein equation from this entanglement entropy
In 3D, probably it's a relatively more manageable problem. As long as you get flat connections, you're done. Such your Simon theory. But if you want Vassiliev equations, good luck.
So is getting the Einstein's equations using this, I mean, is that related to, is it Ted Jacobson's work of deriving Einstein's equations from looking at the thermodynamics of the accelerated observer? Are you familiar with that?
I'm not familiar with that.
Oh, okay.
I would work it out.
Okay, I can tell you more.
Thanks.
I have one more question. So when you have this, your deformed entropy, so from the field theory point of view, I have some extra current around, right? And when you're defining this, should I think of this as sort of changing the definition of what you mean by this H? That you're saying I'm going to shift it away from the rho by this Q integrated on the boundary. That's the idea?
Yeah,
Uh-huh,
exactly.
uh-huh. And then, so can you, does that object continue to have nice positivity properties?
Yes, if you keep mu positive,
Uh-huh.
then it has all.
Then it's fine.
That's right.
Oh, yeah, of course, yeah, uh-huh, uh-huh. Okay.
But we also introduced
Uh-huh.
some imaginary views and yeah.
Mhm. All right.